here. Our next contribution comes from the University of Michigan, and it's a collaboration between L. Thompson, J. Linder, A. Bennett, and B. Carville, and the paper will be presented by Levi Thompson.
Dim the lights a little. First, let me recognize the contributions that were made. This was done while I was an employee of KMS Fusion, so we want to make sure the distinction is there. Over the past couple of days, we've heard several talks concerning hydro desulfurization. By and large, this work is focused on catalysts that are produced by using salts. We've taken a somewhat novel approach to this, attacking some of the problems using sulfide clusters, organometallic clusters. You might ask, why would you use a sulfide cluster or an organometallic cluster? Typically, they're very unstable once they're in contact with the support or either under reaction conditions. However, there are some very beneficial properties that we may take advantage of, at least in focusing on some model studies. For instance, the use of organometallic clusters, by and large, produces very well-defined surfaces. Although many clusters decompose, the surfaces that we produce tend to be somewhat more uniform than those produced using salts. The second major advantage is that we may think about designing a catalytic site. For instance, this work focuses on hydro desulfurization. It's accepted that we want to somehow use a molybdenum-based catalyst. We would like to produce a site that has a promoter. For instance, in this case we have iron. We might also think of using cobalt. The other thing is, from an industrial standpoint, we like to incorporate sulfur so we don't have to pre-sulfide a lot of our catalysts. These are two examples of clusters that were utilized in this work. One, an iron sulfide, and I want to distinguish the monometallic clusters from the mixed metal or bimetallic clusters using the following notations. There's a common thread that links these two. First of all, you'll notice that there are metal-metal bonds. That becomes very important when we think about what we want to produce in terms of an active site. There is controversy as to what the nature of the site for the promoted catalyst is, and we think that these may represent, at least the mixed metal clusters may have some bearing on questions related to the promotional effect. The thinking is that perhaps a precursor that already has, for instance, a molybdenum iron or a molybdenum cobalt bond may produce sites on the surface that allow significant electronic and chemical interactions between these two metals. The other common thread is the presence of bridging sulfide ligands, and it's fairly commonly known that bridging ligands have a tendency to hold frameworks together. This would not necessarily stabilize the metal-metal bond, but we hope to provide very high dispersions by incorporating these sulfides. This slide summarizes a description of each of the cluster systems that we work with. And let's just take an example. Here is the cobalt sulfide, the monometallic cobalt sulfide supported on alumina. We use catalysts that were prepared using organic solvents, so we don't expect to see any problems due to, for instance, chlorine or some other anions that might be produced during preparations using conventional techniques. We looked at monometallic catalysts, a series of bimetallic catalysts produced from monometallic sulfide clusters, and finally a series of catalysts produced from the mixed metal clusters. And again, we were working at using 1 weight % total metal loading. This slide summarizes some of the turnover frequencies for thiophene HDS. And Let's start with the alumina series, and we'll focus on the catalysts that were produced by from the monometallic sulfide clusters. If we take, for example, the molybdenum cobalt system, you can see that the bimetallic catalyst is pretty much an average of the molybdenum sulfide on alumina and the cobalt sulfide on alumina. Not necessarily an average, but it's a combination of the two activity. And this pretty much summarizes the results that we found for alumina, at least in the case of bimetallic catalyst produced from the monometallic sulfides. One very interesting observation was that for many of these, we also noticed significant cracking activities. We should have included C2s. We produced quite a bit of ethane and ethylene during hydrodesulfurization of thiopane. At first, you might expect that an alumina catalyst would in fact produce some cracking activity. However, when we compare this with the MgO series, let me mention that the alumina represents acidic supports, while the MgO is a representative of a solid base. When we compare the alumina results with the MgO result, we see very similar cracking activity. So we can't ascribe that activity for the cracking of thiophene just to the presence of acidic alumina sites. We also see a difference in the intrinsic activities of these catalysts. When we look at, say for instance, the iron molybdenum sulfide, we notice that it's sort of intermediate to the iron sulfide and the molybdenum sulfide. However, when we compare that with the cobalt system, the molybdenum cobalt system, there seems to be a very drastic synergistic effect. In fact, this activity is almost 20-fold more active than the molybdenum sulfide. And it's, as a matter of fact, much more active than any of the alumina series. And I neglected to mention that the activities are reported in terms of molecules of either reactant or product per cluster. For comparison purposes, we've also included Catalco, a conventionally prepared catalyst, Catalco 477. The results here are on a total metal loading basis. One reason why we decided to use a per cluster site density was because we believed that at the clusters at most would produce one active site, so any activities that we report here would be somewhat pessimistic or conservative estimates. The reasons why, for instance, the molybdenum cobalt on alumina, on MgO, responds differently than the molybdenum cobalt on alumina is not well understood. We expected the opposite. It's typically noticed and reported in the literature that cobalt sulfides or cobalt will tend to promote the activity of molybdenum sulfides. The questions raised can in some sense be addressed using the mixed metal clusters. You'll notice that the activities of the mixed metal clusters are much higher, in some cases an order of magnitude more active than either of the bimetallic catalysts or the most active monometallic catalysts. We expect that for these catalysts, again, because they were synthesized from or produced from a mixed metal cluster, we might expect that the interaction and intimacy between molybdenum and cobalt might be a little bit higher for these types of catalysts than we have with the bimetallic catalysts produced from the monometallic sulfides. An interesting way of reporting this information is the turnover frequency as a function of the heat of formation of the bulk metal sulfide. Here for the mixed metal, the bimetallic systems, we've taken an average of the heats of formation for the individual monometallic sulfides. As you can see, there's not a real clear trend here, except that the molybdenum sulfide has a somewhat higher activity. Now, when we include the results for the bimetallic system, we see somewhat of a drastic increase in our intrinsic activity. If we think about what this is telling us, the strength of the bond of sulfur to the metal site has a very significant effect on the resulting activity. It's we typically call this a volcano plot if we had connected the sites, the points for the monometallic and the bimetallic system. This is for the alumina supported series. Now when we look at the MgO supported series, we get more or less what we expect based on reports in the literature. The molybdenum cobalt sulfide has a much higher activity, and again we ascribe this to an effect that, in effect, the molybdenum and cobalt have a somewhat optimum sulfur to metal bond. Now, one burning question is, are these clusters being supported intact? I think the answer to that question is no, although this slide doesn't necessarily tell us that. These are the pure cluster, the molybdenum iron sulfide, in a crystalline state, and then following being supported on the catalyst. And we see that there's very little difference between the two spectra. However, once we start heating the sample up, either in helium, hydrogen, or in vacuum, we notice that there's a very drastic decrease in the band intensities. There's not a shift, but the band intensities tend to decrease, indicating that these clusters are starting to decompose. We also use Moss bar spectroscopy to try and follow the genesis of the materials, and found that for the pure molybdenum iron sulfide, the mixed metal cluster, we can ascribe the iron, that the iron is in a zero valent state. Once we put this on the surface, unlike the IR results, we notice that there's a shift in the isomer shift. And that's the value is indicative of iron being in a 3+ state. So we believe that the difference between these results and the results for the infrared spectra were that these catalysts, or the supported catalyst, was exposed to air, so we believe that it's somewhat air sensitive. We also looked at the behavior as we either calcine or sulfide these catalysts. You'll see, again, starting with the pure cluster, when we put it onto the support and expose it to air at room temperature, we notice the presence of iron 3+ high spin. When we reduce this in hydrogen at about 400 degrees C, we notice the gradual emergence of a second species, iron 2+, and a small contribution from a species that we've, for convenience sake, called iron del+. There's very little difference between the catalyst in the reduced state and after sulfiding. And I should mention that these are all in situ. The spectra were collected immediately following exposure to the reactant or the reducing stream. And we see very little difference between the two. We were somewhat concerned about this Fe del+ species, and part of the answer to that was partially determined by oxidizing this in air at room temperature. We noticed almost immediately following exposure that this spectra collapsed, and we noticed the reemergence of the iron 3+. So it's reasonable to presume that this species is either, the del is either 2 or less than or equal to 2. It's interesting to compare these results with results by Topso and his group. You'll see that for this so-called Comos phase, they report isomer shifts and quadrupole splits that are very similar to what we have. The only problem is that they ascribe the activity to the Fe3+ species. We would tend to believe that the Fe2+ species is responsible for the activity over these molybdenum iron sulfide systems. And let me just quickly summarize some of the SPS results that we have. We've looked at this series of catalysts using X-ray photoelectron spectroscopy, and I'll just go over one example of what we noticed. For instance, for the bimetallic catalyst derived from the monometallic clusters, if you look at the individual clusters, the crystalline clusters, you'll notice that the sulfur peaks have shifted slightly. And these shifts are somewhat consistent with what we would expect for a moly disulfide. Looking at the cobalt, what we would call the promoter atom, we notice that initially the cobalt seems to be very similar. The chemistry may be very similar to that of a cobalt sulfide. However, in following exposure to either the MgO, the molybdenum sulfide, or perhaps after the reaction conditions, after exposure to the reaction condition, we see that we are no longer able to show a similarity between this sulfide and the species that we have in the catalyst. It does, however, bear some resemblance to spectra that has been reported again by Thompson and co-workers for a species that they say contains up to, I believe, 90% of the Como space, one of the leading candidates for the active site for HDS. Okay, I'll just step through and go to our conclusion. The results that we have in the summary is that these types of catalysts are in fact active. We're not interested in looking at commercial, comparing these on a commercial level. We're more inclined to use these as model systems so that we can somehow attack the problems associated with hydrodesulfurization. I might mention that the results seem to indicate if we compare the results for the monometallic systems and the bimetallic system, we might imply an electronic basis for the promotional effect in HDS. There's still this question of what is actually the resting state of either cobalt or iron in these types of catalysts. We would tend to say that it's an Fe2+, although there is some evidence that it may be Fe3+. Finally, results that I couldn't cover, we have looked at using kinetic modeling studies, looked at the activity of thiophene HDS and determined that it may be the rate determinants that may be the hydrogenation of thiophene. Furthermore, we believe that it may be a pi-bonded thiophene based on some tracer studies that we've just recently completed. Thank you.
Time for one or two quick questions. Yes.
So, do you think that the iron molybdenate system is a good model to compare necessarily to the cobalt molybdenate system?
Well,
Thompson work is cobalt source experiments, right?
Well, he did cobalt source and moly iron, and the comparison is very good out of his own lab. So we believe that systems that we might work with, although we're hoping that we can do emission studies, we think that there may be some relevancy for the moly iron system, and that comes right from his work.
If you destroy the clusters, what is the final effect of the initial promoter on the supporting material?
That's not clear. What we hope to do is, with these clusters, produce sites that are very well dispersed and very uniform. So that would tend to make the spectroscopic information a little more, I won't say valuable, but it's easier to understand if the surfaces are somewhat uniform. We can't comment right now on what the structure of what's left behind on the surface is, but certainly, perhaps in the very near future, we may be able to address that question.
Have you tried to follow these quite interesting results by increasing the loading of the metals? All these are based on 1%?
1%, yeah. Actually, we've sort of restricted ourselves based on a couple things. When you use these types of precursors, you don't want to have clusters sitting on top of clusters, because you would expect that after a certain point, then you're going to mimic results that you might get with, say, salt precursors. When you work with the low-loaded catalyst, what you expect, at least for the high surface area supports, is that we'll be able to somehow produce dispersed sites. And then we can address questions as to, say for instance, there's a school of thought that believes that the cobalt stabilizes a molybdenum sulfide. These results, the activities look very similar. We may not need to have that cobalt or molybdenum sulfide underneath. we may be able to do it just with, a few atoms or a very small particle of molybdenum and cobalt, or molybdenum and iron.
We're running out of time, so we'll move on. Thank you for your presentation.